Hello, this is lecture 3 of chapter 2, continuing the transmission line analysis. Basically, in the last lecture, we spoke about the physical insight of the solution that we achieved in the previous lecture. So we talked about how does V of z and I of z change with position. We talked about the RL, G, and C, the physical model of the transmission line, and how that determined alpha, beta, and gamma, which is alpha plus j beta, and the characteristic impedance z naught, the propagation constant, complex propagation constant gamma, and the characteristic impedance z naught. And the solution we had was in this form, and we saw also the time domain solution, the same equation that we've seen before in the earlier chapter. We spoke about waves that travel to the right in the positive z direction, attenuate this way, and waves that travel backwards and attenuate in the opposite direction, obviously. And these were the V plus and the V minus waves. This is a case of lossless line where the two waves were traveling back opposite to each other without attenuation. In this lecture, we're going to talk about something we call the reflection coefficient, which we going to be named gamma. This Greek uppercase symbol gamma, as opposed to the lowercase symbol of the lowercase gamma, which was alpha plus j beta. All right, so gamma uppercase here is the reflection coefficient. We'll talk about gamma of z as the ratio between the negative traveling wave and the positive traveling wave. How much of the wave here travels back? So we will define gamma as the ratio between the negative traveling wave and the positive traveling wave. V minus e to the plus gamma z divided by V plus e to the minus gamma z. And here's our definition right there in this equation 2.43. Alright, so based on that definition here, I go back to this expression here and take V plus e to the minus gamma z as a coefficient here, and I'm left here with 1 plus this ratio here would becomes gamma of z. Alright, and I of z similarly will be similar thing. It will be that 1 minus gamma of z. So with that, my expression now don't have a V minus anymore, because the V minus now is being expressed in terms of gamma and V plus. Alright, 1 plus gamma, 1 minus gamma. These are the expressions for the voltage and currents in the frequency domain. This driving point impedance is the ratio between V of z and I of z at any location of the line. In other words, it's the impedance looking this way by the wave itself. How much impedance is seeing the voltage divided by this current. That's called the driving point impedance. The driving point impedance is basically going to be the ratio of z divided by I of z. These things will factor out, and you'll be left with z naught times 1 plus gamma z. Well, here it is, z naught 1 plus gamma z over 1 minus gamma z. This expression here is very, very important, and you better pay attention to it, because this will be used a lot, and actually basis and foundation for what you'll learn later, this Smith chart. That impedance looks like a function of position. It's V of z is a function of position, gamma of z is a function of position. It's a function of position. The impedance as the wave travels is going to see a different impedance at different locations on the line. If I manipulate this expression here, z of z is equal to that, I can rewrite gamma of z in terms of the impedances. And this also is a very important expression here, as it represents the inverse or the reciprocal of this equation here, the reverse manipulation of this expression here. So here, if you know gamma, you can get z of z. If you know z of z, you can get gamma of z. If I look at the ends of the line, z of 0 and z of L, the impedance at the input side, which is the z is equal to 0, and the L side, which is the load side, and I ratio V of 0 divided by I of 0, I get this expression here. And if I ratio V of L divided by I of L, I get that expression here. Alright, this is related to the reflection coefficient at the input side, and this is related to the reflection coefficient at the load side. But guess what? V of L over I of L, as we've seen before, is basically the impedance Z sub L right here, the ratio between the voltage and the current here. While the voltage and current here will be the input impedance here, which is going to be the driving point impedance at the input side of the line itself. So that's Z of Z right there. Well, this one here is Z sub L. Now the load is supposed to be known, right? Z sub L is supposed to be known. So based on that, I can find gamma at the load side, gamma of L. All right, I know Z naught. Z naught is what? R, L, G, and C, and the frequency. Remember that. Z naught is a characteristic number given for the transmission line. We know it. So if I tell you what the load impedance is, you can tell right away what's the reflection coefficient at the load end is. And this expression here is rewritten right here. Z sub L is equal to Z naught 1 plus gamma of L divided by 1 minus gamma of L. And I can get the reflection coefficient by manipulating this one here to be in that form. ZL minus Z naught divided by ZL plus Z naught. Guess what? If ZL is equal to Z naught, no reflection. If ZL is not equal to Z naught, there will be a reflection. If the line is mismatched, that's how we say it. If the load is mismatched to the characteristic impedance, we get reflection. But if the load is matched to the characteristic impedance, equal to the characteristic impedance, there will be no reflection. All right. Now that we know gamma of L, we know gamma at the end of the line, knowing the Z sub L. We know gamma here. Guess what? I can find gamma everywhere else because I can go back to the definition of gamma. Gamma is right there. Gamma of Z is equal to that. So if I know one location on the line, I can get the rest of them. And here's the expression. Gamma of Z is equal to V minus V plus, V plus e to the minus gamma Z. So gamma of L is equal to that. And if I know gamma of L, I can get the ratio V minus over V plus. And if I know the ratio V minus over V plus, I know gamma of Z. So guess what? I can manipulate all that to be gamma of Z is gamma of L equal to that. So knowing gamma of L and knowing the location that I would like to calculate things at, I can get gamma of Z. So we have a full solution now. Let's go over this again. I gave you R, L, G, and C, so you know the line gamma and Z naught. I give you Z sub L, so you know the reflection coefficient here. I gave you Z sub L, here it is. If I give you Z sub L, you can get me gamma sub L. If you know gamma sub L, I can get you gamma of Z. Now that you know gamma of Z, you can find V of Z and you get I of Z. Except for the V plus. We haven't really determined the V plus yet. Alright? Who's determining the V plus? The source has to determine the V plus for us. Okay, let's stop here for a minute and go back to the frequency domain equations that we are talking about here. V and I as a function of position. Everything in this expression is known except the V plus and the V minus. As you recall, we mentioned that the parameters gamma and Z naught are supposed to be known. That's R, L, G, and C, and the frequency on the line. That determines for you the gamma, the complex propagation constant, and Z naught, the characteristic impedance. The only thing unknowns here are the V plus and V minus. These were the solution of differential equation. Second order differential equation, we end up with two constants. To get the constants of a differential equation, we need boundary conditions. Well, where are the boundaries? Here's one boundary, here's another boundary. That's a line, that's a solution. We have one boundary as interface between the source and the line, interface between the load and the line. So these are the two boundaries here. And these two boundaries here, if we use them, we can get the knowledge that we need about the V plus and V minus. And that's exactly what we've done here. If you look at what we've done, we started with the load end. We applied the boundary condition here. We said to the line, here's your ZL. So the line told us, here's my gamma sub L. All right, here it is. I gave the line ZL. The line told me what gamma of L is, the reflection coefficient of the load. The reflection coefficient of the load determined how much of the wave reflects back. So I got the V minus term because that's how much in terms of V plus. V plus is yet to be determined, and that has to be determined by the other boundary condition at the source end, which we haven't discussed at this point in this part. However, if you recall in the previous lecture, we did apply the boundary conditions on both ends mathematically, and we're able to find V plus and V minus. Here we try to be a little bit more physical by starting by the definition of the reflection coefficient at the load end and how does that affect the reflection coefficient everywhere else. The only thing missing in this development here in this lecture so far is how much is V plus. Well, we have two choices. You can go back and get it from the previous lecture, or you can work out your KVL around this loop here and get it here, which is going to be similar to get the same expression. If you work out the KVL around the input side loop, around the source end, you can actually get the V plus, and the development is right here. You can check it out for yourself. Basically, based on that, we can actually find the voltage at 0, the voltage at the load. We also can find the current at 0 and the current at load. In fact, the rest of the chapter on transmission line, and actually most of the transmission line development, focuses more on the gamma, the reflection coefficient, rather than the amplitude of the signal or the V plus on how much signal is traveling. The gamma relates to the waves reflecting on the transmission line, and that matters the most in applications. Now, with the general solution that we have achieved so far for a general line, we got the V plus, we got the gamma, we got Z naught, all that. Let's talk about special cases here. Two special cases are very important interest: the infinite line extending to infinity, and the matched load line. Matched load means the load is equal to the characteristic impedance of the line. You recall we mentioned something about the matched load here is no reflection coefficient, no reflection on the line. Basically, you'll find out that the infinite line is the same thing, and these two special cases are somehow related to each other. For both cases, you will discover that the solution is in the form of a V plus e to the minus gamma z, and the current is basically the same thing divided by Z naught. In other words, you only have a V plus wave, no V minus wave. The ratio between V of Z and I of Z, which is the impedance of the line, will be simply Z naught, because this cancels that, and you only be left with Z naught. That means your Z of Z, your driving point impedance, anywhere on the line is equal to the characteristic impedance at all locations, including the input impedance of the line. If you solve the boundary conditions, you can get your V plus. That's one of the easy cases here that you solve, and basically you will have only one wave traveling from the source to the load, no reflections. The next special case that I want to talk about is a case that produces standing waves. That's interesting, because right here we only had waves traveling in one direction. That means we have traveling waves. These are standing waves. That means waves are not going anywhere. What does that mean? Well, in fact, you have waves traveling from left to right and waves traveling from right to left, and the two waves will interfere to cause a stationary pattern. Let's look at this in the time domain, because whenever we want to see something physical, we want to see it in the time domain. Here is a V of Z of t, V plus cosine, V minus cosine. We are ignoring attenuation for the time being. This wave and that wave combine with each other. I place some manipulation here and end up with this expression here. Look at this expression that I have now. Something times cosine omega t minus beta z plus something else times cosine omega t times cosine beta z. This part here is nothing but the traveling wave, and again omega over beta is your phase velocity. Alright, as time changes, position changes. Here, as time changes, the amplitude changes. The position change and time change and multiply by each other. So there could be a location where that cosine is equal to 0, and no matter what happens to the time, the amplitude here is still 0. And it could be another location where the cosine is equal to 1, and the time variations here basically change the amplitude. So the nulls of this component here are not going to move. The nulls here, or the zeros, are going to be moving. The phase is constantly shifting in this case. While here the phase is not going to be shifting. When a position has a 0 magnitude, it's not going to go anywhere. So let's grab that so we can see it a bit more physical. Alright? The first part is the traveling wave with a constant magnitude. Here's the magnitude, cosine that. So if I just look at the magnitude of this, here it is. That's the magnitude part. Alright? Imagine that this line here is the magnitude part. So the wave is actually filling this part of the diagram. Obviously there's a cosine variation here, but it's traveling, so the magnitude is right there. Superimpose on it things that has a magnitude that would go to 0 at certain positions. Alright, so if I look at this part alone, here it is. This part alone is right there. 2v minus, that's this part here. 2v minus is the amplitude, and it has time variation, but whenever this is 0, nothing changes. At these locations here, nothing changes. Whenever the cosine is equal to 0, the time doesn't produce any change, but at the peaks of the beta z, which is 1, you get a variation with time. So this goes up and down with time. So this is the magnitude or the amplitude of that part. If you combine this with that constant, you get this combined diagram right here. Okay, that's your combined diagram. So you have peaks and valleys, peaks and valleys, peaks and valleys. Traveling part and a stationary part. The stationary part is what we call a standing wave, and this here is a traveling wave, and the combination is basically a mixed wave that combines the standing wave and the traveling wave. We define the standing wave ratio as the ratio between Vmax. Vmax is this amount right here. That's your Vmax over Vmin, and that's your Vmin. So at different locations, you can see here's Vmax and Vmin, Vmax, Vmin. That ratio is called the standing wave ratio. For a pure traveling wave, gamma is 0, no reflection. That's my pure traveling wave. Remember that? Vmax and Vmin are the same everywhere. Vmax and Vmin are the same. In this case here, your standing wave ratio is 1. While if you were to talk about a pure standing wave, that's pure standing wave. Vmax is right there, Vmin is 0. So the ratio between Vmax and Vmin is going to be infinity. Standing wave ratio is infinity for a pure standing wave. That was the case for a lossless line. For a lossy line, the signal is going to be attenuating, and actually the traveling part is decaying, and the standing wave is right there, and the superposition looks like this. And basically, if you talk about Vmax over Vmin, you will find out that that changes from one position to another. Vmax over Vmin. The standing wave ratio will not be the same everywhere. Typically we define the standing wave ratio for the ratio between Vmax and Vmin near the load end of the line. Another way of looking at the combination of the two traveling waves and the interference that happens and the standing waves that result or the mixed wave that result is to look at the two components, the V plus e to the minus gamma z and the V minus e to the plus gamma z, and see how they mix with each other. Again, to simplify the story, we're going to look at them in a lossless situation where alpha is 0. So we're looking at V plus e to the minus j beta z and V minus e to the plus j beta z. The alpha is being 0. These are basically two phasors. The phasor V plus multiplied by a phase change, and the phasor V minus multiplied by another phase change. I'm going to assume that I'm going to start with a location. Let's say right here. Look at this diagram here. These are the two phasors. The two phasors, suppose at some location they are in phase with each other. Some location, I call this Z1. Now, let's look at the phasor V plus. Here's V plus. The phase changes in the negative fashion, and the rate of change is minus beta z. So at some position Z2, we would have rotated that much angle right there. This one here, the phase changes in the plus sense. So the V minus goes this way instead of going the opposite way. So at some location, Z2, this would change by a certain phase. This would change by the same exact amount of phase in the opposite direction. So that's how they look like after a certain phase change, after a certain distance. So at location Z2, here it is. At some location Z3, they will probably be against each other like that, okay? This continues to rotate, this continues to rotate, this becomes up, this becomes all the way down. Now, here is the new location Z3. At some location Z4, this would rotate another 90 degrees, this would rotate another 30 degrees, they will be there, and so on and so forth. So the two phases are rotating against each other. This one rotates this way, and this one rotates that way. So at one point they add, at some point here they subtract. Right there they subtract. Right there they both add in the negative sense. So if I look at the sum of the two phasors, when they were along each other, the sum would be basically the sum of the magnitudes. When they are opposite each other, they will be the difference, and then when they go at this location here, they will be like that. So if you look at the diagram here, you will see that the Z1 is where they both are along each other. They add up to a maximum right there. At the point Z3 right there, that would be the minimum. It would be the difference between this one and that one. And at point Z4, they will be both negatives, and they will add up the same magnitude as the positive ones. So the diagram here for the voltage, you can see is going up and down, and there will be maxima and minima, maxima and minima, and so on and so forth. That's a mixed wave situation, which is basically what we saw earlier in the diagram that we drew for the mixed wave. Now suppose the two are equal to each other. The V plus and the V minus are equal. What's going to happen is when they subtract here, they will give you exact 0. And the maximum will be twice as much, and the minimum will be 0. Now I'm showing here the magnitude maximum, so whether it's positive or negative, they both have the same magnitude. Well, obviously if the V minus and the V plus are experiencing an alpha, an velocity situation, the V plus continues to shrink and the V minus will increase. And as a result, you'll never have an exact 0, and you'll never have a constant peak value. Things would be changing in a fashion of this nature here, like we have discussed before.